So today we're going to start talking about variability, standard deviation, and those types of things. So why is the study of variability important? It's virtually in everything. Whenever we did our goldfish activity, every time we took a sample, we got something different. Like we did not get 40% every single time, even though the true proportion is 42%. So it allows us to distinguish between usual and unusual values, and we can report, if we only talk about the center of a distribution, it's not giving us an accurate view of the entire thing.
How do you know what the actual distribution of something is if there's variability?
So the variability is based on different samples. So each dot on here is a different person or a different sample, different part of my data. And we use all of it together to predict what the population is. So when we take different samples, we get different things. But our goal is that by averaging them all or by looking at it, it gives us a clear view of the entire population.
Okay.
So looking at A, B, and C, they're all symmetrical, which means the mean and the median of all three of these would be what? The same, which would be what number? 45. Good. So, but they all three look very different. So what's the difference between A and C?
C is more closer together.
Yeah, C is closer together and A is further apart. So the range of A would be 50. The range of B would also be 50. And the range of C would only be 10. But do A and B look exactly the same? No. There's more data points in the middle for B. So that's why even saying what the range is isn't always the most accurate, because A and B look very different even though they have the same range. So that's why we're going to start talking about standard deviation. And I just talked about that. So the range is different for A, B, and C. A and B have the same, C is different. So once we start looking at the standard deviations, that's going to be different for A, B, and C. We look at what a deviation is first. That's the root of the word. Deviation is just how far each data point is from the mean. Then we will average all of those together to find the standard deviation. And I'm just going to kind of skip this because it takes a lot. The estimated average of the deviation squared is called variance. People don't really ask for variance very often, but variance equals standard deviation squared. So then your question is, well, why do we even have variance if nobody asks for it? If I asked you to calculate standard deviation by hand, then you would end up having to find variance first and then square rooting it. So let me show you the formula, and then I'll kind of explain why. So if you have, this is the formula for variance, S squared. When you get this number, you have to take the absolute value of it because some of the deviations are positive and some are negative. So let me show you just kind of a picture of what this looks like. When you add them all up, these are the actual deviations. Some are positive and some are negative, and then they add up to 0. So if I added all of these together and tried to find an average, I would technically just be finding an average of 0, which wouldn't tell me anything. So what you have to do is square each of these numbers first, because when you square a negative number, it becomes positive. And then turn them all positive, so you square all of them, then find the average of these, then go back and square root them. So the calculator does all of this for us, but if you're thinking about doing the process of standard deviation by hand, you're squaring all of the standard deviations, finding the average of those numbers, which is your variance, and then square rooting it back to so it's kind of like the absolute value of your distances from the mean. Yes?
Why would you square? Why just not make the negative into positives and then calculate that?
Because I don't know. That's a good question because that's what they did. I think it just has to do with the average not being as accurate, but I really don't know the answer to that question. But essentially, if you were doing it by hand, you would square them all, find the average, then square root. It's a good question. Yes?
When would we have to do this by hand?
Never? I'm just explaining you why we have variance. Why? Yes. What we've already done. So typing it into a list and then doing the 1-bar stats, and it gives that to us.
So it's one of those things that it gives.
I'm going to talk about it in a second. So the next thing is standard deviation. This is the formula, or this is the vocab of it, the actual definition, the typical deviation from the mean, or the average deviation from the mean. So if we had variance, the way we would find it would be by taking the square root. And then opposite of that, if we had standard deviation and it said what is variance, then I would need to go back and square it. So on your little chart, go back to the very beginning page where you had that T-chart. We're going to add some more. Did we already do standard deviation? Not yet? Okay. So on the left was population and on the right was sample. So we're going to add 2 more below. The first one is going to be standard deviation. On the population side, it's going to look like it's a lowercase s in Greek. It's called sigma. And it kind of just looks like a curly O. And then on the right, it's for a sample standard deviation, it's just S. Then for variance, it looks like sigma squared and S squared.
What's the difference between a big sigma and a small sigma?
A big sigma is like finding the sum of something. So that's the summation notation. A lowercase s is going to be for standard deviation. So the bottom, you might want to star this. If I said, what does this standard deviation mean in context? That would just be the sentence that I would want you to write. It deviates from the mean by an average of blank. Yes. So just adding context to whatever we're talking about. Now, on the calculator, when you did the 1-bar stats, if you guys want to pull that up with the menu that we had, I told you guys that the only things that showed up were the population standard deviation and the sample one. So if you want to go back to your menu, you can hit Stat Calc 1, and you'll have all of those things pulled up. And what you should have is, there's a space, and I don't have it pulled up, but there's a sigma x, and then there's an SX. And they're 2 different numbers. So does anyone still have the data in from last class? Sean, do you have it? Okay, can you tell me what the sigma x was? If you go back to Stat Calc Enter. Just go out 3 decimal places.
2.244, I think. Wait, 2.188.
2.188?
Yeah.
Okay, and then what was the SX?
2.244.
244. Okay, so your sample standard deviation, which is which one? Which one's my sample?
SX.
The SX. This is my sample. And this right here, the top one, is my population. They're always, in the calculator, it's always going to give you both options. And it is up to you to decide, what is my problem talking about? Is it giving me a sample or is it giving me population? like I said, 9 times out of 10, it's giving you the sample. So you're going to choose which one? The SX. And there's like that one time where it tells me that I'm using a population. So you really have to read your context clues closely and decide, is everybody included or is it just a sample from them? The reason why, so your sample is always going to be a little bit bigger than your sigma or than your population. And the reason why, I'm just going to show you, and I don't want you to write this down, I want you to just look. The formula for sigma is the square root of the sum of the deviations squared over n, and the S is the same formula over n minus 1. So by just looking at the two formulas, why is S going to be bigger than the sigma one, numerically? Because I'm dividing by less. So this denominator is always going to be 1 less than the sigma one. And that means, like, if you have a smaller denominator, then it's always going to be bigger. It'd be like if this were 1/3 and this were 1/2, which one's bigger? The 1/2, right? So that's the case every single time. And I'm going to talk about in a second why the denominators are different, but that's just kind of in your head as to why the sample one is always bigger. And so there's that. The reason why is because when you have a sample, you have this thing called degrees of freedom. And degrees of freedom is the number of independent observations that are free to vary. In this unit, degrees of freedom is always equal to n minus 1. So I want you to write that down. N minus 1. N is your sample size.
Is the denominator from standard deviation?
Mm-hmm. So the best way that I can explain this, and this is talking about fish, but I'm going to use it in the context of this classroom. So let's say that there are 6 people in here, and I told you guys that the average, like for this next test, the average has to be an 85. It has to be an 85. So 6 of you are going to take this test, and 5 of you make different grades. So 5 of you can make whatever you want. Maybe there was a 75, 100, a 32, 100, and 100. Okay? So I've got these 5 people. And that average of those 5 people is an 83 or something. So that means that that 6th person is no longer allowed to make whatever they want. They have to be a fixed value. They have to be a certain score in order to make the entire average of the 6 people be an 85. So when I say degrees of freedom, that means 5 people n minus 1. 5 can do whatever they want. They have all the freedom. But the 6th person is a fixed value. And so, and if you don't remember any of that, or if that doesn't make sense, the takeaway is your degrees of freedom is n minus 1. Because n minus 1 people, everybody except one person can do whatever they want. But in order to get the outcome that you need, that last person has to be a fixed value. And that's just to make the sum of your deviations equal 0. Yes? So you use this like to calculate standard deviation. Like I said, we don't do that by hand. But once we get into running tests for means, like in second semester, you'll need it for that too.
Like in real world scenario, when would you use this?
Well, it's just for calculating the standard deviation by hand. But the reason why they have to do n minus 1 is essentially it kind of gives you some wiggle room. So the sigma is like very accurate. It's like, this is my population and I have everything in it. The sample gives yourself a little bit of wiggle room. That's why it's a little bigger than the population one. so that I'm not 100% positive this is a standard deviation, but this is me guessing it. The next measure of variability is the IQR, which we already talked about. And the IQR is also resistant to outliers. So go back to at the bottom of that blank page where we talked about measures of center and spread. My next T-chart, I had mean and median. So I had mean and median on the left, and I said that the median was resistant to outliers. That means it's not affected by extreme values. So now talking about the spread, we have range. We have standard deviation. We have variance and IQR. And then IQR is like your middle 50%. It's like the range of just the middle part, the middle 50%. So I know that IQR is resistant to outliers. Would any of the other three be resistant, do you think? Or if I added a really extreme outlier into my data, would that affect them all? Let's just go through one by one. Range, is it going to affect my range? Yes. Extreme will definitely affect my range. Standard deviation, yes. And variance is just standard deviation squared. So whatever standard deviation does, variance does.
Why does it affect standard deviation?
The standard deviation? Just the standard deviation is based on the average distance from the mean.
Okay.
So if I have all of my data here, my standard deviation is going to be really, really small because the distance from the mean is only like 1 away right now. But if I add this person in, that means that my average distance from the mean now has this guy to play in the factor. So it's going to affect my
Average distance from the mean or
the mean.
Okay.
So now it's going to mess up my mean, and it's going to mess up my standard deviation. Okay, I'm going to skip this. I feel confident in your IQR. Without doing it by hand, what we would do, if hypothetically, so I'm just going to talk through this because I don't want to waste our time. I would put everything into a list, and then I would do the 1-bar stats. And how could I, using the stuff that it gives me, how could I find the IQR? Because it doesn't give me the IQR, but I can calculate it. What would I do? Yeah, so I would just do Q3 minus Q1 in my calculator because it gives me the Q3 and it gives me the Q1. So there's 2 things we've seen that the calculator doesn't explicitly give me, but I have to do myself. The first one is variance. How would I do that? I have to square the standard deviation. It gives me that. I just have to go in and square it. And then it doesn't give me IQR, but I would have to do what? Q3 minus Q1. So those are 2 things that I could ask you on a quiz or a test or something, and you would be looking through your calculator menu and you're like, I don't see it. That's because you have to actually do the math from what it does give you. So, gonna skip that. Okay, so transitioning to the next part. The last part of today, we'll be talking about linear transformations and combining 2 sets of data. What does that do to my mean and my standard deviation? So I want you to turn, I don't know exactly what page this is, but turn to where you see, I should say like the Lion Stat Company or something like that. Page 62. Okay, so 1700, but I'm not going to put X bar. It's going to be what? mu. And then which one do I use? The 603, because it is a population. So then the next part says that business was good. Is that what it says? And so everybody gets a $500 raise. So instead of going through and adding 500 manually, because that's going to take forever, I'm going to go to Stat Edit. I'm going to go back into my list. And then I'm going to go to List 2. Doesn't matter if it's blank or not. It's going to override it, so it doesn't matter. And then I'm going to go up to where List 2 is highlighted. Then I'm going to hit Enter. So you'll just see this like blinky square. It's kind of like a formula for Excel. You can type in whatever you want, and it's going to copy it over from List 1. So what I want to do is create some sort of formula that takes List 1 and adds 500 to it. So I need List 1 plus 500. To type in List 1, I'm going to go to the second button, second 1, plus 500, and then hit Enter. So what it's done is it's copied List 1 and then added 400 or 500. So now I can just do a 1var stats. So stat calc enter. But I want to change this list to now list 2. So second 2. Enter. For the rest of the problems, you can now just do right over list 2 and just keep using list 2 the whole time. So if you want to go on to the next one, you'll do stat edit and just copy over, hit enter, and type in your next formula. I think you're subtracting.
Cut 500. Are we cutting from the 500?
You're cutting for everything's cutting from the original. Everything's cutting from the original.
How do I switch this to list 1? Should I just
Clear it and then hit second 2. So what happens when I just add and subtract numbers? So what happens to the mean and what happens to the standard deviation? So when I add and subtract, like I'm adding, everybody gets a $500 raise or everyone is cut by $100. What happened to the mean each time? It went up or down. So it changes up or down. And then what happened to the standard deviation? It's the same. Doesn't change. And so think about, because this is always kind of a hard topic for people to understand. Think about, I have all of your test averages on, dot plot like this, and it ranged from a 50 to 100. And then I decide I'm going to give everybody a 5-point raise. Imagine me picking up your grades and shifting over 5 points and then dropping them back down. So now it would be from 55 to 105. Did the spread of it change? No, it's like I just picked them up, moved them over, plopped them back down. So the spread never changed, but my average went up 5 points. Okay? What about when I am multiplying and, I guess, dividing? But what happens when I multiply? Both of them change. So they both are multiplied by whatever the factor is. So they either both got doubled or they both multiplied by a factor of 1.3. So think about this same thing, 50 to 100, and I give everybody a 10% raise on your test. The person that made a 50 would end up getting a what if I had a 10% curve? A 55, but the person that got 100 would end up getting 110. So did my spread change from, it was originally 50 to 100, now it's 55 to 110. It did change. So, no one gives a curve by percentages because it's hurtful to the ones that scored lower. It's helpful to the ones that scored higher. So that doesn't make any sense. But when you're changing things by a percentage, that means that everything is changing, mean and standard deviation. So those are, and I think on your PowerPoint, it talks about it again. Why is it on that slide? Skipping. So here are the two rules. You can just highlight them in your notes if you want, but we kind of wrote the rules already. Here's an example of how you will see it on a quiz or test, like in a context of a problem. So it says an appliance repair shop charges $30 service call to go home for a repair. It also charges $25 per hour for labor. From past history, the average is an hour and 15 minutes. And the standard deviation is 20 minutes, including the charge of the service call. What is the mean and standard deviation for the charges of labor? So from what it gives you, it wants you to create a y equals linear equation. So basically like my base charge plus something times per hour, like mx plus b here. So what is my base charge? $30. And then plus how much per hour? 25x. And the mean and standard deviation, so mu and sigma, of the average and standard deviation time is 1.25 and 0.33333, or 1/3. You might just want to write it as 1/3. It doesn't matter. Either way. I would accept either. So basically now it gives me the average time, but I want to find the average and standard deviation cost. So essentially this formula is a cost versus time formula. Inputting the average time and the standard deviation time will then output the cost or charge for labor. And so with my mean, I know that it changes by addition and it changes by multiplication. So to find my mean cost, I'm just going to say 30 plus 25 times 1.25. And that's going to get me a number, which I think is 61.25. Just saved you the time calculating that. So my average cost is $61.25. But my standard deviation is a little different because does that $30, like adding $30, does that affect a standard deviation? Adding and subtracting? No. So when I'm doing my standard deviation cost, I ignore or I leave out the $30 because all I'm concerned with is multiplying it by 25. So I would say 25 times 1/3. And I leave out the adding and subtracting part because that does not affect my standard deviation. You end up getting 8.33. So if I were to interpret this, I would say the average cost for labor is $61.25, and the typical deviation from that $61 is $8.33. That's the average of how much deviation is from the mean. Questions about that? Okay, next one is, so I don't know if you guys have heard from last year's class, but we played a game called Statland, and it was so impactful that we put it on our class t-shirts last year. So you are about to embark on the journey that is Statland, and it is the most fun game that you will ever play in your whole life. You will go home and play it every day. You'll play it with your friends. It is so much fun. So turn to page 63. 63. So when I did A plus B, what happened to the means? The 2.5 and the 3.5, what? They added, yeah. So the means add.
In order to do A plus B, do I have to do a list 3 with like L1?
No.
What do we do?
Oh,
just the numbers.
yes. So for A minus B, when I did A minus B, what happened to the means? They subtracted. So for means, it is super, super easy to add and subtract the means. You don't have to do all of that stuff. You're given two means, you either add them or you subtract them. With the standard deviation, it's a little more complicated, so I'm going to show you the formula. The standard deviation is you can even check it if you want, you're going to square them, add them, and square root the whole thing. No matter if it's added or subtracted. So in this game, you should have gotten the same standard deviation both times. When you added and when you subtracted.
Why did you square them and then square root them? Why can't you just add them?
Because you square them, add them, you square root, which would be different than just adding them together.
So these should be the same number.
Yes.
That's what we're saying.
Yes, which they are, because you use the 2.041 here. Oh, that's for your first set of data. Yeah, they should be the same if you did it correctly. So the big thing is that you should always, always add, even if it's like the second part of the game where you subtracted them. You always add the middle. So in your notes, I want you to go to them right now and say, always add on your PowerPoint.
What should the number be?
2.041. Always, always add, no matter what, even if it's the sum or the differences. You do have to have this equation memorized. So you square you add the variances and then you square root the whole thing. The difference between the first activity that we did and the second one is that linear transformation is when I'm talking about one set of data. So I'm just going to make a little note that you can write in your notes if you want. Linear transformation, which was that Lion Stat Company, is when you have one set of data and you're adding, subtracting, multiplying to that set of data. Like I'm manipulating it. The Statland game, which is the most fun you've ever had in your whole life.
Yes.
The Statland game is when you are combining data. So you basically have two or more sets of data, and you're either adding or subtracting them together. So the second rule was whenever you have multiple sets of data, usually two, but maybe more, and you're combining them together. So that's how you know which rule to differentiate from. So let's look at an example of combining data where it's talking about bicycles arrive at a bike shop in boxes. Before they can be sold, they must be unpacked, assembled, and tuned. So we want to find the total average and standard deviation for these bicycles, the total process. So for the means, if it's the total, for the total mean, I'm just going to add all of these numbers together. Should I then divide by 3? Yes or no? No. How come? Because I've already done it. I've already found, I'm finding the average of the averages. I do not need to divide by 3 because I want the total time. So if I asked you, what is the average time it takes you to get ready in the morning and get to school, you would consider the average time it takes you to brush your teeth, get dressed, drive to school, walk inside. And then to find that total time, you would add all 4 of those things together. Would you then divide that by 4? No, so it doesn't make sense. I'm asking you for the total. So don't go and divide it by the number. You're just adding them together. So 3.5 plus 21.8 plus 12.3. To find the total standard deviation, I'm going to use my formula where it is 0.7 squared plus 2.4 squared plus 2.7 squared, square root the whole thing. So you're squaring and adding them all together and then square rooting the whole thing. And here it is, prettier. Okay, the very, very, very last thing we'll do today, I promise, I know it's been a long day, is graphing box plots. And these are super easy, so just bear with me for another 10 minutes and I will get through this. But the last graph that we'll learn how to make is box plots, and this is what we'll use for the rest of the semester, so rest of the year. You will really never make a histogram again, and you'll really never make a stem and leaf for any of those graphs that you learned first chapter. The only graph you're really going to make from here on out is a box plot. And they're so easy to make because your calculator does them for you. So advantages of box plots are you can actually see when you have an outlier or not. So there's no like, oh, is this an outlier? I can't tell. It kind of looks like one. There's none of that. A box plot actually shows them and calculates them for you. The only thing is you can only use a box plot when you have more than 10 data points, okay? Only when you have more than 10. Otherwise, you'd want to use a dot plot or stem and leaf. A modified box plot, a skeleton box plot we don't ever use. I don't even know why it's in here, but it does not show outliers. So I just want you to circle skeleton and say doesn't show outliers. The reason why we have it on here is because in your calculator, a skeleton box plot is an option, and that's the one you don't want to choose because you'll draw it incorrectly. So I'll show you in a minute on your calculator what that means. You will cuss on these, so you will cuss on the box plots. Here is an example of what it will look like. A modified is what we'll use in this class, where it does show outliers. And it has points that represent the outliers. I want you to circle this. Oh, I don't know where it went. I want you to circle these 2 equations. And those are how you calculate outliers by hand. You do need to memorize this because sometimes I won't give you the full set of data. I'll just give you like this piece of information and I'll say what are the outliers. Yeah, it could be. So I'm trying to get through it. Then the whiskers extend to the largest or smallest data point. That's not an outlier. So do you guys have this picture on your PowerPoint? Okay, so we're going to label some things. The first thing is your minimum point. So this is our minimum, which is 17. And our maximum, which is 47. So that's our max. Our box in the middle is our IQR, essentially. So this first line is going to be our Q1, our median, our Q3, and then this data point here is like the end of our whisker, because on the sides we're calling those whiskers. And that is the last data point that occurs in my sample before I get to an outlier. So on the left side in green, those are how we calculated outliers. So I'm just going to fill in what the equation was. The 24 and 30, those represent my Q1 and my Q3. Then you subtract 1.5 times my IQR and add 1.5 times my IQR. That's just the formula. 1.5 times your IQR. And the 15 and the 39, those represent the imaginary or invisible fences that basically anything outside of those fences become an outlier. So I'm just going to go ahead and dash those, 15 and 39. So everything within those fences are good. They are not outliers. Anything out of those then become an isolated dot. So that's why 47 is a dot, because it is an outlier. You do not draw the whiskers all the way out to the fences. You just draw them out to the data points within the bounds. So I don't have a 39, but what do I have? A 38. So this is 38. I do not draw anything in between 38 and 39 because I don't have it. I don't have a data point that's 39. So I just go to the next lowest one, which is 38. Now your calculator will draw this for you. The reason why we learn how to make one by hand is because sometimes AP questions will not give you every single data point. They will just give you these 5 numbers. And they'll say, create a box plot from it. So that's why we have to learn how to make it by hand as well. If I were to describe it, we're going to cuss. So the median is 26, range of 30, outlier at 47, a right skew. So I'm going to show you in a second how we decide what the skew is based on a box plot. Here are all the symmetrical ones. Notice that the median is in the middle. And then the IQR represents the width of the box. So why, it doesn't look bigger, but it is. Why is this box a little bit bigger than the first two? Why would the IQR be a little bit bigger based on what the histogram looks like?
The edges have a high number.
Yes, so the edges are really high. If you ever see a distribution where the edges are super high, this is the largest standard deviation, largest IQR. It's kind of like the worst thing possible because you've got really high frequency on the edges and then not much in the middle. So you would choose the answer choice that has like the biggest standard deviation, the biggest IQR, because those are the furthest away because my mean is right here. And if my standard deviation is the distance from the mean, a lot of people are very far from the mean. Whereas the first two are more symmetrical and just kind of even. A skewed box plot would look something like, oh, why is it being weird? Meaning like it has a longer tail. I don't know why it's doing that. There we go. So what you'll do is you'll take the median and you'll draw a line there where the median is. Then you draw an arrow out to the very, very end. And for instance, if I had, you don't have to draw this, but I'm just going to visually show you. If I had an outlier right here on the left-hand side, then this would now make it a left skew. So you're going to go all the way out to the outliers on both ends. Whichever arrow is longer makes it the kind of skew that it is. So if it's longer on the left, it's a left skew. Longer on the right, it's a right skew. But you always start from the median. Yes?
It goes out to the outlier.
Mm-hmm.
So why didn't the last one go out to the outlier? Like the one on 51.
The one on what?
Oh.
Well, we didn't say the shape on that one. But the shape on the last example would have been a right skew. Are you talking about this last example that we just did where we labeled it?
Yeah.
We didn't say the shape of it, but if I did say what the shape was, I think it said a positive skew on the cussing part. But it would also be a right skew.
Yeah. So we don't extend the whiskers out, but the arrows?
No, just whenever we're deciding what the shape is. But, oh, are you talking about, yeah, don't draw the whiskers out. But when you're, and I don't even draw the arrows anymore, I just look at it. But if I think the distance from the median to the outside, if it's longer on the right, it's a right skew. Longer on the left is a left skew. So let's look at some comparative box plots, and then we'll make one on the calculator, and then we'll be done. Here is the salaries in 2009-2010 of different NBA players or NBA teams. And we are going to look at or discuss how to comparatively cuss on something like this. So when I'm cussing, I look at the center first. So let's compare the medians. And I'm just going to highlight the medians so you guys can see. Which team has the largest median? The Knicks. Which one has the smallest median? Nuggets. So I would say the Knicks have the largest median, the Nuggets have the smallest. The next thing is outliers. Which two teams have outliers? Lakers and the Grizzlies have outliers. Okay, the spread. So looking at the range, I'm going to go from the min to the max for all of the ranges. So which one has the smallest range? Well, the Grizzlies goes from here all the way out to here. So you have to go out to the outlier. So the Knicks would probably have the... No. Yeah, the Bulls. So that would have the smallest range. Which one would have the largest range? Lakers. Yeah. And then for, what's the last S? Shape. Let's go through each one and name the shape. So for the Bulls, what kind of skew do we think? Right? I would also accept symmetrical because it's not completely right skewed. But what about Lakers? Right? Because it goes all the way out to the end. Knicks? Good. Grizzlies? And Nuggets? Right. So when you're comparing the shape, you basically just have to go through and list all the shapes. You could group them together if you wanted. Like these four have right and one has symmetrical, but you wouldn't have to. So the last thing I want to do is create a box plot on our calculator. So everyone take, let's see, what data do we have in there right now? We don't have a lot. You cleared it? Okay. Let me find some data that we can put in that isn't a ton of data. And that might. Is there any on our homework? Let's see. Go to page 65. Oh, okay. Yeah, so let's go to page 65, and let's go ahead and put set 1 into our calculator. And I'm going to hit second, y equals, And this is where all of your stat plots will be held. So I only want plot 1 to be turned on. The rest should be off. I'm going to hit enter.
Wait. Can you just go back? How do you get to that?
Second y equals.
Y equals was one of the 5 at the top.
Yeah, second y equals. Hit plot 1. So plot 1. You should be at this menu right here. Make sure that the on is selected. If it's on the off right now, just click on the on. Then for type, you're going to have to hit the right button. You can't hit the down button. You have to hit right 3 times to where this bottom left one is selected. Now this is where there's a difference between modified and skeleton. We will always use this one right here. We will never use the box plot next to it because it doesn't show outliers. And why would we want a box plot that doesn't show outliers? It makes no sense. So you will never, ever, ever use the middle one. Always use the one with the dot. Your X list should say L1. So I'm going to change mine by hitting second 1. Keep frequency as 1 and keep mark as 1. From there, you're going to hit graph.
Instead of frequency,
No, you're not going to hit graph. I'm sorry. I have slept over the summer. You're going to hit zoom stat, which is option number 9. So after you have everything set up, you're going to hit zoom 9, and it should show up. So you don't have to go back and do the 1-bar stats. If you want to get all of your information, you can just get it in the graph. So if you hit the trace button, hit trace, and then scroll to the right, it actually gives you all of your 5-number summary right there.
Honestly, take it.
Yeah. So
So for homework for 65, is that what you're asking?
yes.
Draw it
So for 65, I want you, or page 65, I want you to draw them all and then give me the 5-number summary on them.
Wait, draw and draw.